It's been a long day yesterday. I feel your pain, but if I have managed to grade your tests, so if you go into WebAssign, you'll see what the updated score for it is. What I haven't had time, because that takes even longer, is to collect all your information and put it into my spreadsheet so I can give you your real grade. Do not pay attention to what WebAssign says your grade is, because it doesn't actually calculate it correctly. WebAssign will tell you what your homework is, and that's fine. It'll tell you what each individual test that you've done is, and that's correct. But when it aggregates it into the overall score, it's wrong. Because I put weightings on homework and in tests, and WebAssign doesn't. It basically thinks everything's worth the same. And that tends to inflate your grade to make it seem better than it is, unfortunately, but that's what it does. So what are we going to do? Well, Chapter 7 is our next, over the next 2 weeks. The main theme of Chapter 7 are integration techniques. Right now, we've got in our little tool bag, I've got a good memory, which basically means you memorize standard integrals. You just know that the antiderivative of e to the x is e to the x, and that secant squared gets you tan x, and so on. That would be your first line of attack, and you use it a lot. And included in that, I would put the power rule, so we know how to integrate 5x cubed. And then the second major pillar of technique that you've got in your little tool set is u-subs. Really powerful, really big. Use that a lot as well. So we are, over the next 2 weeks, going to find other techniques. So this is the first one. This technique is called integration by parts. And it's roughly the product rule for integration. So what it allows us to do is it allows us to integrate a function that's made up of two functions of x multiplied together. And the formula, just like the product rule has a formula, in Calc 1, the formula for a product was f dash g plus fg dash, right? Well, in integration, the integration of f of x g of x is f of x capital G of x, take away the integral of f dashed of x to capital G of x d of x. And in fact, the proof of that, if you go and look for it, is that they use the product rule in reverse. So they say, here's the product rule. If we work backwards, what would it tell us? And this is what it tells us. So how do we apply the product rule for integration? In other words, how do we do integration by parts? There's a huge difference from Calc 1. In Calc 1, when you do the formula and you plug in all the bits, you're finished. Apart from, make it look pretty, right? Factor it and make it look like the original. But in integration, and this is more of a process, because as you can see over here, isn't the formula still got an integral in it? So it's not that uncommon for integration by parts to be a repeated process. In other words, you keep doing it until this little bit at the end turns into something that you know the answer to. So here are my steps. Oh, by the way, capital G of x is the antiderivative of g. Step 1, choose who f and g is. That was never a problem in Calc 1. Couldn't you make the first guy f and the second one g, and that was it? You never thought about it. But not now. When you do integration by parts, there are many situations where one of them has to be the f and the other one has to be the g. And I'll be talking about that in a few minutes, about how you decide. Analogy. Do you know when you do u-subs, don't you have to decide who the u-sub is? Because very often there's choices. Well, in this case here, you might think, well, there's not much choice. Well, there is. You can make the first one f, or you can make the second one f, right? There is a choice. And one of them very often will work, and the other one won't. And so we have to figure out how we decide which one works and which one doesn't. I guess you could simply just pick the first one is f and the second one is g. And then after 5 minutes, you'll say, this isn't working. And then you just throw that piece of paper away and you go back to the question and you switch places. I mean, that technique, I guess, could work. I don't like that technique, but I guess occasionally that might have to be done. So you pick your F and your G, you then apply the formula, which is step 2. And then step 3 says, keep doing it until you've got an answer. Essentially, keep doing it until this little bit here is something you know the answer to. So eventually, see this little bit here, all this f dash g of x stuff? This will eventually be x cubed, or e to the x, or sine x, or something like that, that you can get the answer to. So let's jump right in. Oops, just dropped my pen. I'll start off with a nice easy one. I think is easy anyway. The integral of x sine x dx. Now, right now, with the tools that you know about, isn't that question impossible? You can't do a U sub, and it isn't in your table of standard derivative, antiderivatives, right? So you'd be stuck, but not today. Today we have a new guy in town. So I'm going to call this guy F, whoops, this guy F and this guy G. Now, according to our formula, it should be f of x, capital G of x, take away the integral of f dashed x, capital G of x, d of x. Okay, let's see. F of x is x. What's the antiderivative of sine x? Antiderivative of sine x. What is it?
Negative cosine.
Take away the integral of f dashed of x, which is 1, with the antiderivative fella, and it looks like this. Now, all I'm doing in this line is tidying things up a little bit. I'm not actually changing anything. This is negative, so is that. You put them together, and 1 times this guy gets you the cosine of x. Now, do you see that this integral is actually a doable one, right? I don't need to do anything else except get its answer. So what I now have is negative x cosine x, and the antiderivative of cosine is sine x, and then remember to put your plus c. Pretty good. Any questions about that? That seemed to go reasonably smooth. Now, when you look at the answer, I think it would be very difficult, if not impossible, for you to guess that the antiderivative, because that's all an integral is, right? That the antiderivative of this is that. Would you agree that we can't, you know, we needed this technique. We can't just play about with it and guess until we get something. So here are some of the rules about who F and G is. So before we do any more examples, let's give you rules about who you pick for F and who you pick for G. If your function looks like a power of x followed by any trig function, right, sine, cosine, that kind of stuff, or any power of x followed by e to the x, you know, e to the 2x, things like that, then choose your f of x to be the power. So if you have to do x cubed cosine x, x squared e to the x, right? Things that look like that. Choose this fella. All right. If your function looks like this, if it has a log function with some x's, x squareds, x cubed, anything like that, square root of x, don't matter. Choose your f of x to be your natural log of x. So do you see sometimes the power of x is f of x and other times it's not? Now, in general, if you can't integrate one of the functions, make that function your f of x. Let's give you an example of what that might look like. Can't think of any right now. That'll do. Don't remember what works in. Do you know the antiderivative of the inverse sine of x? The answer is no. I do not know what the antiderivative of that guy is. So you make him the f of x. Do you know the antiderivative of log x? No, we don't. We know that 1 over x has an antiderivative that's equal to log x, but we don't know the antiderivative of log x. That's why you pick that one. So the general rule, which is kind of vague, says you've got two guys multiplied together. If one of those two guys cannot be integrated, make that one the f of x, no matter how weird it looks, make it the f of x, and the other function, make that the g of x. And that'll typically get you out of trouble. I guess you could say, well, what happens if you can actually, just where I'm going next, if you can integrate both. So what do you do if I can find the integral of f and I can find the integral of g? Then this is your rule. Choose f of x so that its derivative is simpler. So what do I mean by that? Well, suppose you had x cubed sine x, for example, right? X cubed sine x. Can't you integrate x cubed? Yeah. Can you integrate sine x? Yeah. But if you differentiate x cubed, doesn't it become 3x squared, which is a little bit simpler than x cubed, right? It's went down a power. So I guess I'll call that rule A, call that rule B. There's a rule C. Suppose you get an integral that's got e to the x in one of the trig functions, right? E to the 2x in one of the trig functions, right? Something like that. Then doesn't matter. Pick either one for f of x, you'll be fine. I'm not putting the last one in because it's a silly choice. Choice D or situation D is, what happens if you can't integrate either f or g? What do you do? Well, the answer is, you don't do integration by parts then. In which case the question is silly, right? Okay. So let's do some practice. Before I do, I want to show you a little trick. I'm going to show you a shortcut. The linear shortcut method for integrating trig and exponential functions. And the reason I want to show you this is it's a nice little shortcut that saves you time. The reason this shortcut works is that you technically are doing u-subs. Linear means that the thing you're doing it to has to be linear. It has to be 2x plus 1, 4x plus 7, right? This shortcut doesn't work for x squareds or x cubed stuff, right? But for linear functions. So here is the shortcut. I can tell you the antiderivative of all these exponential functions. The antiderivative of e to the 2x is e to the 2x. What fraction goes at the side?
1/2.
Yes. E to the 4x will get you e to the 4x. What fraction? Quarter. E to the 6x plus 1 will get you e to the 6x plus 1, and the fraction you'll get is 1/6. Do you see how this shortcut is working? Do you see how it allows you to integrate e to the 2x plus 1 or 4e to the 6x plus 1, right? It's just a shortcut. If you don't remember this or don't feel you're comfortable in remembering it, can't you find all of these answers by u-subs? But that means you have to take another piece of paper at the side, figure out what the u-subs is, and then bring it back. And you know, it's a couple of minutes off your life, but it's not disastrous. Now, you can also do it for trig functions. Show you how the linear shortcut method works. Basically, you integrate it as if it was an x, and then you figure out what fraction to go at the front. Now, if you integrate a sine, don't you get a negative cosine? What fraction should go at the front to compensate for the 3x plus 1?
1/3.
Yes. Do you see it's the same basic pattern as e to the 2x? You get a half. Now, cosine of 4x plus 2. Well, if you integrate a cosine, you get a positive sign. And what fraction will you get this time?
1/4?
Yeah. Do you like this shortcut, or is it more confusion than help? If you like it, you use it. If it's more confusion than helping you, then you just do use subs like you always have. Right, for the last one, what would the integral of secant squared get us?
It's a tangent.
It is. So you're going to get the tangent of 3x take away 2. And what fraction are you going to get the front this time?
1/3.
There is a flow to this, isn't there? It's not just random. There is a reason why you get the fraction that you do. And if you don't believe me, just differentiate all those things and you'll find out it works. Right, we're comfortable with that little skill building shortcut trick. Okay, let's return to doing some questions. So here is one that's like question 1 from the homework. It's going to be the integral of x e to the 9x dx. Okay, who's F and who's going to be G? Which one of these two is F and which one of these two is going to be G?
X is F.
Right. Can you remember it belongs to one of the rules that I mentioned earlier. I think it was Rule. Now, in this question then, f of x is this guy. Okay. Now we need to integrate e to the 9x. Can you see that my shortcut is going to help me here? The integral of e to the 9x is definitely e to the 9x times what fraction?
1/9.
Put a little bracket around that. Are we comfortable with where the capital G of x came from? Subtract. Well, if you differentiate this guy, you get 1, and you still get the same guy that you had a minute ago. And all I'm going to do in this line is make it look pretty. Now, this fella here, right? This guy is doable now, right? I can find the antiderivative of 1/9 e to the 9x. See if we can make this happen. Okay. If it was just e to the 9x, wouldn't I get 1/9 e to the 9x? But since it's 1/9 of e to the 9x, what fraction goes here?
Is it 1/81?
Yeah, it's 1/9 times a 1/9. And so I don't have to rewrite that. We just did it all in one go. Can you see you've now got the answer? So you want to find the antiderivative of this product using integration by parts. We got you. This one is like question 2. Okay, who's going to be the F? Who is going to be the G this time?
The cosine.
What's the cosine going to be?
The F.
So if you want to pick this one as F, then what's going to happen to this guy? This is going to be the G, right? So let's think this through. If that's going to be the g, won't I integrate this? Right, that's what you do with g. And if you integrate this, doesn't it get bigger rather than simpler? So remember,
Okay.
so make this your f and make that your g. Typically, if you have a choice between powers of x and a trig function, make the powers of x your f, and that tends to get you out of trouble. Now, this one has a different problem. This is the first time we're going to find out that in integration by parts, you don't always get the answer you want right away. You have to kind of do it again. So let's see how that works out. F of x is this guy, so we won't do anything to it. If you find the antiderivative of cosine, you get positive sine. That's working out fine. Take away the integral. F dashed gets me 2x add 2 and sine x. Do you see that what we have here isn't finished? How do you think I'm going to find the integral of this new guy?
Do the same process.
You do the same process. So that's why integration by parts is more like a process and less like a formula. To me, in a formula, you just plug things in once and you get the answer. But in a process like this is, don't you have to repeat it until you do eventually get your answer? So that's going to be x squared plus 2x followed by a sine x. Take away. I guess I'll put a big bracket around that to make sure that I don't get the signs wrong. Who am I going to pick for the f and the g now? In this question, who's the f and the g going to be now?
G will be sin x.
Yep. So whatever theme you start with, keep that theme all the way through the repeated processes. So if you're always picking the trig function to be g, keep picking the trig function to be g until you get to the end. Now in this case, it's going to be f of x, which is that guy. The antiderivative of this is negative cosine. Take away the integral. The derivative of this is 2. This fella is negative cosine dx. And now I've got negative of things inside other things. That is just a recipe for me to screw up. So this is what I would do in the next line. Some people choose not to. But I would just take care of this, tidy it up. So this is negative, so that makes it a positive. Now watch this one. This is a negative of a negative of another negative. You see that? This is negative. The negative of this makes it positive, but this itself is negative, and that's why I now have a negative 2 cosine x dx. There's just too much happening there for me to try and keep it, juggling in the air. So all I've done in this line is tidy things up. We're almost finished, aren't we? Because this term is good. The one next to it is good. And what's the antiderivative of 2 cosines?
2 sine.
And so take away 2 sines and add a c. So the antiderivative of this horrible thing is this even more horrible thing. And I don't think you'd ever guess that by just trial and error. You see that there's no way of avoiding having to use integration by parts. You really can't avoid it.
Professor?
Yes.
I'm confused on the second to last line, how the integral of 2 cosine x is not negative.
How the integral of this is not negative.
Going from the line above to the line below.
Okay,
You
here we
kind
go.
of explained it, but I got confused.
Right. there's a negative
Oh,
of this guy, which makes it positive, but then there's another negative cosine in here. So 3 negatives together makes the whole thing negative,
yeah, I missed that other negative on the outside. That's what it was.
right? Yeah. But it's easy to do. That's why I try and make sure I do this line, even though it means I have to write a lot more. It just helps me to get my signs. If nothing else, it helps me get my plus and minuses in the right place.
Yep, thank you.
Are we cool?
Professor,
Yes, Matthew.
I was wondering, if we were to do this problem on the homework website, would they like want us to multiply the terms?
No, I would want you to just leave the darn things alone.
Okay.
I mean, you could, but there's no great advantage, because if you did that, can you trust me, it'd be even uglier looking than it is right now.
Mhm.
Now, let's see what we got in store, because there's lots of nuances we haven't even touched yet. Oh, okay. Here's a nuance. That guy. But wait a minute. I need 2 functions. That's only one. It's log x. So how can I possibly use integration by parts when there's only one function? Well, you kind of make it 2 functions. Slightly artificially, but we still do it. Have you any idea how I could rewrite that as 2 things rather than 1 thing?
Times 1?
Yeah, and typically you stick the 1 at the front. So if you ever get a question in integration by parts and it's only a single function that you're being asked to use, rewrite it as 1 times that function. So it's going to be 1 times log x, 1 times the inverse sine of x, right? 1 times whatever the function is. Now, again, when that happens, you get a little sub rule. And the sub rule is make that guy f and make the 1 a g. So make the original question, whatever that single thing is, make that the f and make the g the 1. Now, if you think about it, why that must work is, if I knew what the antiderivative of log x was, couldn't I just write down the answer and I wouldn't even need to use integration by parts? So it's pretty obvious I don't know what the answer to the antiderivative of log x. And by the way, it's not 1 over x, if you're thinking that. The antiderivative of 1 over x is log x, but the antiderivative of log x is not 1 over x. Its derivative is, but not its antiderivative doesn't exist right now. So this is going to become f of x, capital J of x, take away f dashed x, capital J of x, d of x. That guy gets left alone, right? And what is the antiderivative of the number 1?
X.
Take away the derivative of log x. What is the derivative of log x?
1 over x.
And g of x is x again, dx. And then something really cool happens. I like the x at the front, so I'm writing the x log x. Isn't 1 over x times x just 1? And what does that get me? Well, that gets me x log x, take away the antiderivative of x, which is 1, plus a c. There is something just elegantly sneaky about that strategy. I didn't know what the antiderivative of log x. I'd be a really good guesser if I thought it was that. But you can differentiate that. And trust me, when you differentiate that, you get log x. So It's kind of cool. Let's do another one with log x in it. At this time, it's got two functions, right? It does an x cubed and it's got a log x. Who do we choose for the f and who did we choose for the g now?
F is
Who do we
still
choose for it?
natural log.
Yeah. Now you might think, oh, that's going to cause trouble. No, it's not going to cause any trouble at all. Right, leave that guy alone. Integrate x cubed. Differentiate that guy. Integrate x cubed. Make that look a slightly prettier version of itself. Won't this cancel out one of the x's, and now you're going to be integrating 1/4 x cubed. But we know the answer to that guy. He's a power rule question. Add 1 to the power, divide by the new power, which is why I get 1/16, plus c. Do you see that we now have a mechanism where any power of x you like times a log x, we can get its antiderivative? So I'm going to do one more log function, and then we'll move over to other situations. But since I have this to do, I'm going to pick a really ugly one. X squared, the natural log of x squared. Now that's going to be f of x, capital G of x, take away the integral of f dashed x, capital G of x, d of x. Now, one of my rules, the last rule I gave you was, if you have two functions, one of them you cannot find the antiderivative of, then the one you cannot find the antiderivative of has to be your f of x. Which one of these two, the x squared or the log x squared, which one of these two do you not know the antiderivative of? Because that's going to be your f. So which one can you not find the antiderivative?
Natural log square.
Right, so you make that whole thing, including the square, as your f, and that guy over there is your g. Do you see how we chose what I chose? Does it make sense that that would be the f and the other would be the g? Now, if you switched places, can you trust me? It would take you maybe a line or two before you realize this isn't working. Right, it just gets weird and you don't know how to finish it. That's normally a sign you've picked the wrong f and g. That sounds like I swore there. You picked the wrong f and g. Nobody got that one. It just struck me as sounding weird. So let's see. Leave this guy alone is your f. So that's that guy squared. Integrate this fella gets you 1/3 x cubed. Okay, can live with that. I'm going to differentiate the natural log of x squared. Now that means you have to remember chain rule. Agreed? This is a chain rule world. And so 2 log x times the derivative of log x, which is 1 over x. So if I differentiate log x squared, I will get 2 natural log of x's times 1 over x. Are you comfortable with the derivative part gives me all of this? Followed by the integral of this guy, which is 1/3 x cubed dx. So tidying this one up by just basically switching the order that I write them. 1/3 2, what's that going to get me? 2/3. I like the x cubed first because it looks pretty. Natural log of x dx. Okay, what am I going to do now is I'm going to have to work on this. My L looks a bit weird. Right, there we go. Don't I have to do integration by parts again? Who am I going to pick as f?
ln.
Right, remember the rule, stick to the guy that you started with, right? So that saying something about leave the party with the person you came with, right? So that's F. This is G. It's going to get a little bit messy here, but that.
Shouldn't that be an x squared?
Oh, well caught. Well caught. Yes, it should be. Now, oops. I meant to put a bracket there. This whole thing, we're going to do this too. I just didn't want to write that again. So this fella, leave him alone. Integrate 2/3 x squared. You get an x cubed with a 3, so you get 2/9 x cubed. Subtract the integral. This fella, if you differentiate him, gets you 1 over x. This guy is 2/9 x cubed again, dx. 1/3 x cubed natural log squared. Take away all of this. 2/9 x cubed natural log of x. Take away a negative makes this thing a plus. Cancel out an x, and you get 2/9 x squared dx. Whew. And then you get this guy, take away that guy, plus add 1 to the power, divide by the new power, c. That is one ugly looking answer, isn't it? That is one ugly looking answer. But at least we can get the, you know, the antiderivative, which is what we're looking for. Are we good? A lot to absorb here. While I'm getting ready for our last question, you want to say hi for attendance? Let's do another example of a single function. This time it's not log x on its own, it's the inverse sine of x on its own. And we are going to find its antiderivative. Okay. Now, when there's a single function on its own, don't we do that one times trick? Which one of those two, the 1 or the inverse sine, is going to be my f of x?
Sine inverse x.
Aren't we doing the one you can't get the answer to as your F in these questions? So it's pretty much, isn't it, when it's a single function, isn't it going to be the single function is going to be the f of x every time, just the way it works out. Now let's see what we got here. F of x is, leave that guy alone, oops. And the antiderivative of 1 is x. I'll bracket around that. Take away the integral. Okay, this one's going to test your knowledge. The antiderivative of inverse sine of x.
Is it 1 over the square root of x plus 1? X squared plus 1?
Darn close. You're in the right ballpark.
Is it minus?
It is. It's 1 minus x squared.
Yeah.
Times the g guy, right? Capital G of x dx. Now I'm just tidying this up. X's really look better at the front. Take away, and I'm not really doing that much with this fella. And then what you might not have expected will happen sometimes. This thing here is no longer going to be an integration by parts method. To get the integral of this, integration by parts is not the way to go. But we do have a technique for finding the integral of this guy. Great. What's the technique that we use?
U sub.
U
solution.
sub.
All right. And who will the U sub be?
1 minus 2x.
1 minus.
Sorry, x squared.
Yeah. You're thinking of the next line, I suspect. Right. So differentiate, and you get this. Crossover. You get this. Isolate the dx. You get this. Actually, I'd probably be doing this in a piece of scratch paper at the side rather than my main working, right? Because when I'm finished, won't this just get replaced by its answer and we're done, right? But since I've kind of started in that, I guess I should complete it. I'm just going to get the positive version and then just remember to stick a negative when I'm finished. So this fella here, well, you have an x, you have a square root of u, and you have a negative 1 over 2x du. Well, I've changed my mind. I'll bring that negative in. Right, that negative's there. I'm going to bring it in because it's going to match nicely with this one, and the x's are going to cancel, and I'm basically going to be left with that, which isn't too bad, right? You know, this negative and that negative cancel, so this is going to be a positive answer. I hope I have enough room to squeeze it in. There it goes. Okay, we still have to deal with this fella, don't we? But we'll hop around it. What do we need to rewrite this as in order to get its integral? One over the square root has to be written as a fractional form, right? What fractional form?
Negative 1/2.
So I can add 1 to the power and divide by the new power, which is really nice because it cancels with that guy. And that turns into what? The square root of u. And that turns into the square root of 1 minus x squared. I know it's a bit crushed, but the antiderivative of inverse sine of x is x inverse sine of x plus this ugly square root that we just found. Is that cool or what? I mean, this is such a, I just love this technique. It is such a smooth, sneaky way of getting antiderivatives of products. Right. Now, it's not as clean as the product rule back in Calc 1, right? There's choices about who the F and G is. It's not as clean as Calc 1, because in Calc 1 you just do the process and you're finished. In these questions, don't you very often have to do the process twice or combine it with another process or whatever. And so it's a little bit sneakier, but the pluses are we can now find integrals, antiderivatives, of a lot more functions than we could have done before we started today. If I gave you all the questions we did today and said, here, find the antiderivatives, but I gave you, before I told you this, wouldn't you look at them all and say, can't do them? They're impossible. Don't know the answer. I have a U sub, but none of my U sub ideas work. And it's not a standard integral, so you might just say, well, give up. That's what's kind of, the guy who figured it out, and I use guy as both girl and boy, the guy who figured that out must have been one of those people who said, no, I'm not just going to give up. It ain't possible, it can't be done. I'm not going to do that. I'm going to figure out some blinking way. It looks like a product rule to me. So I'm going to figure out what that product rule should be. And that person figured out the method called integration by parts. And now we have a whole big, huge chunk of functions that are no longer, we can't do them. And I think it's pretty impressive.